Dear students, now we are going to discuss about correlation. Correlation is of two types. One is cross correlation, the other one is autocorrelation. Now we can see the correlation is in fact very similar to that of convolution. So very similar to that of convolution. Cross correlation of two signals is a measure of similarity between those signals. So if you consider the cross correlation, that is the measure of similarity between two signals. That means how much one signal is related to the time delayed version of another signal. Okay. How much a signal is related to the time delayed version of another signal. Now let us see the equations. Now there are two types of equations. One is for energy signal, that is a periodic signal. The other one is for power signal, periodic signal. So if the signals are real signals, then the cross correlation is given by R12 of tau, which is equal to integral minus infinity to infinity x1 of t, x2 of t minus tau dt. Okay, x2 of t minus tau dt. Okay, so we can see, we know that നമുക്കറിയാം ഈ കൺവല്യൂഷൻ ഇക്വേഷൻ എന്നുള്ളത് ഇതുമായിട്ട് വളരെ സിമിലർ ആണ്. കൺവല്യൂഷൻ എന്ന് പറയുമ്പോൾ എന്താണ്, ഇന്റഗ്രൽ മൈനസ് ഇൻഫിനിറ്റി ടു ഇൻഫിനിറ്റി x1 of tau x2 of t minus tau d tau ആണ്. But here it is integral minus infinity to x1 of t x2 of t minus tau dt ആണ്. Okay, now if the signals are complex, then the cross correlation R12 of tau is equal to integral minus infinity to infinity x1 of t x2 conjugate of t minus tau dt. Similarly, R21, the correlation, cross correlation of second signal to the first one, integral minus infinity to infinity x2 of t into x1 conjugate of t minus tau, x1 t minus tau conjugate dt. Now, if the signals are power signal or periodic signal, then the cross correlation equation is given by limit t tends to infinity 1 by t integral minus t by 2 t to t by 2 x1 of t x2 of t minus tau conjugate dt. So here there is a slight difference from that of the energy signal. So here we put it as limit t tends to infinity 1 by t integral over a t. Similarly, the cross correlation R21 of tau, limit t tends to infinity 1 by t integral over t x2 of t x1 of t minus tau conjugate into dt. So this happens when the signals are complex signals. Okay, when they are complex signals. But most of the signals which we consider are, or basically for these tutorial problems, we consider signals having signals which are real. So we only need to use this equation integral x1 of t x2 of t minus tau dt. Okay, now let us see some of the properties of this correlation. This R12 of tau, the cross correlation between 1 and 2, is equal to R21 minus tau conjugate. This is known as a conjugate symmetry. Okay, that is true in the case of power signals as well. R12 of tau is equal to R21 minus tau conjugate. Okay, so that is conjugate symmetry. This R12 tau and R21 tau are conjugate symmetry. Second property, R12 of 0. When tau is equal to 0, R12 of 0, there is no delay here. Then if that is equal to 0, then we can say that integral x1 of t x2 of t conjugate dt is equal to 0. That means the two signals are orthogonal. Here, if the cross correlation is equal to 0, for tau is equal to 0 and cross correlation is obtained as 0, then the signals are orthogonal. That means integral x1 of t x2 of t conjugate dt is equal to 0. So similarly, in the case of power signal, R12 of 0 is equal to, if R12 of 0 is equal to 0, that means the limit t tends to 1 by t integral x1 of t x2 of t conjugate dt is equal to 0, means then also those two signals x1 of t and x2 of t are orthogonal. Similarly, the third property R12 of tau, whose Fourier transform will be equal to x1 of omega into x2 of omega conjugate. So the Fourier transform of this cross correlation is given by x1 of omega into x2 of omega conjugate. That is the same in the case of power signal R12 of tau. The cross correlation is related to the Fourier transform of the signals x1 of omega and x2 of into x2 of omega conjugate. Okay. So, but we know that in the case of convolution, x1 of t convolution into x2 of t will be equal to what? X1 of omega into x2 of omega. But here the cross correlation x1 of omega into x2 of omega conjugate. That is the cross correlation. This cross correlation is the similarity between any two signals x1 of t and x2 of t. Okay, x1 of t and x2 of t. The second one is the autocorrelation. The autocorrelation function is a special form of cross correlation function. It is defined as the correlation of a signal with itself. Now this autocorrelation is a correlation of a signal with itself. Okay. So if we consider in the case of energy signals, so look, in the case of energy signals, what is the equation? So this is R11 of tau, or it is also known as R of tau, that is equal to integral minus infinity to infinity x of t into x of t minus tau conjugate d tau. So here both not x1 of t x2 of t illa. In fact x1 of t into x of t into x of t minus tau conjugate dt. So that is very similar to that of cross correlation, but here the signal with a delayed version of itself. Now tau is called a delay parameter. Now let us see some of the properties of this autocorrelation. Autocorrelation is also conjugate symmetry. So R of tau is equal to R of minus tau conjugate. So it also satisfies the conjugate symmetry principle. Now the second one, the value of autocorrelation function for an energy signal at origin, that means tau is equal to 0, is equal to the total energy of that signal. So R of 0, that's R of tau with the tau is equal to 0, is equal to energy of the signal, which is integral minus infinity to infinity x of t whole square dt, mod x of t square dt. Okay, so at t is equal to tau is equal to 0, if you find the autocorrelation with the tau is equal to 0, that means R of 0, that is equal to the energy of the signal. Finally, third property, autocorrelation function R of t and the energy spectral density psi of omega of energy signal form a Fourier transform pair. That means R of t R of tau a Fourier transform, the autocorrelation the Fourier transform psi of omega, that is known as the energy spectral density function. Okay, energy spectral density function is the Fourier transform of the autocorrelation function. This is also known as autocorrelation theorem. So this is also known as autocorrelation theorem. Now let us see the relation between convolution and correlation. So there is a much similarity in the case of the equation of convolution and correlation. So there is a striking resemblance between the operation of convolution and correlation. So because we have already seen R12 of tau is equal to what? Integral minus infinity to x1 of t, x2 of t minus tau dt. But x1 of t convolution x2 of t is what? Integral minus infinity to infinity x1 of tau, x2 of t minus tau d tau. Hence we can say that this R1 of tau is equal to x1 of t convolution x2 of minus t with the t is equal to tau. Okay, with the t is equal to tau. Okay. x1 of t convolution x2 of minus t. That will be the that will be the cross correlation of the two signal. Okay, so they are related in this way. Now if we can see that if one of the function is an even function of t, that means if x of t is an even function, that means x2 of t is an even function, that means x2 of t is equal to x2 of minus t. Okay, this x2 of t is taken as an even function, that is x2 of minus t is nothing but x2 of t. Okay, then we can see that the cross correlation and convolution are equivalent. Then they both of them are equivalent. So this is the relation between convolution and cross correlation. So in this lecture we have seen, in this video we have seen correlation, both cross correlation and autocorrelation, and also we have seen the relation between convolution and correlation. Thank you.